Mumbai is one of the largest Indian cities. Recently, a study about temperature differences in localities a few miles apart in Mumbai made headlines in the news. So, Powai recorded temperatures nearly 13 degrees cooler than the densely built up neighborhoods of Ghatkopar. Why such a stark difference? If you look at a satellite image of Mumbai, you might notice that Powai appears greener than all of its surrounding areas. And there's more to that green than just a pretty view. So if you're thinking this vegetation has something to do with keeping Powai cooler, you're right. Cities often replace natural landscapes with concrete, asphalt and glass. These materials absorb and retain heat, creating what we call as urban heat islands or UHIs. The urban heat island effect isn't just uncomfortable. It increases the risk of heat stress, dehydration, and leads to higher energy use, especially during peak summer months. One powerful way trees help cool their surroundings is through a natural process called transpiration. Transpiration is when plants release water vapor through tiny pores on their leaves, known as stomata. As this water evaporates, it absorbs heat from the air, cooling the area around the plant. Kind of like how sweating cools our skin. A single mature tree can release 100 to 500 liters of water into the atmosphere every day through transpiration. This process not only cools the air, but also plays a role in cloud formation and even rainfall patterns. But here's the question. Is the plant doing this just to help cool the earth? Of course not. Transpiration plays a critical role for the plant itself. The plant spends water through transpiration to transport nutrients and water upward, to cool itself, to get carbon dioxide for growth, and to stay healthy. In this lesson, we'll zoom in literally on the stomata, the microscopic pores that regulate both gas exchange and water loss in plants. We'll learn how to observe stomata up close, and then we'll explore how their structure and distribution are tied to essential processes like transpiration and osmosis. So let's get started and see how much of life is happening on the surface of a single leaf. So we'll observe stomata using a method which is easy yet effective. So all that you're going to need is a fresh leaf. When I look out of the window of my living room, I see an evergreen ashok tree. I chose this leaf, but you can pick any leaf which is accessible to you. You'll need a clear nail polish, transparent tape, microscope slides, a marker, pair of scissors, and a compound microscope. Let's start by comparing stomatal density on the upper and lower leaf surfaces of the ashok leaf. Apply a thin layer of clear nail polish to both the upper and lower surfaces of the leaf. Wait for a couple of minutes for the nail polish layer to dry. Once it dries, stick a transparent tape on both sides. As a good practice, always label your slides. Next, carefully peel the coat of the nail polish with the tape and transfer it to the slide. You should be able to see the clear layer of nail polish on the tape. Repeat the process for another side of the leaf. Let's view the lower side of the leaf under 10x objective. Do you see tiny shining buttons spread over the entire field of view? These are stomata. Now, let's zoom in with the 40x lens. You can see the guard cells now. Entry and exit from stomatal spaces are gated by these specialized cells. Like the purple vacuoles of Riscantia, guard cells also have a vacuole. When guard cells actively transport potassium ions into their cytoplasm, the water potential inside them becomes lower than the surrounding epidermal cells. As a result, water enters by osmosis, the guard cells swell and curve, and the stoma opens. When potassium ions exit, the reverse happens. Water leaves the cells, they become flaccid, and the pore closes. This mechanism allows the plant to regulate how much carbon dioxide it takes in for photosynthesis and how much water vapor it releases to the air. Now, let's calculate density of stomata on the lower surface of Ashok leaves. Firstly, we'll count total number of stomata from 3 fields of view under the 10 and 40x objective. Next, we'll note the average number of stomata for calculation of stomatal density. Density is number per unit area. Therefore, to calculate density, we must estimate area covered by the field of view. So let's use our eyepiece reticule calibrations for this purpose. In earlier lesson, we've calculated one reticule division at 100x to be 0.125 mm. Diameter of field of view is equal to 11 reticule divisions. Therefore, diameter of field of view is 11 multiplied by 0.125, which turns out to be 1.375 millimeters. Using this value of diameter, we can estimate the area of field under observation to be 1.485 millimeter square. Similarly, diameter of field of view at 400x magnification turns out to be 0.363 millimeters, which means we are seeing 0.103 millimeter square of area here. Using these areas and our stomatal count, the lower surface of the Ashok leaf has an average stomatal density of about 293 stomata per millimeter square. In many plant species, stomata are more abundant on the lower surface. This reduces water loss because the lower side receives less direct sunlight and less wind exposure. So, is the stomatal density lower on the upper surface of the Ashok leaf? Let's look. At low magnification, nothing obvious. At higher magnification, still nothing. If you spotted no stomata, you're right. In our observation, the Ashok leaf had stomata only on its lower surface, a pattern which is common in many tree species. Environmental factors such as light, humidity, carbon dioxide levels, and water availability influence stomatal density and transpiration rates. So, go ahead and design your own experiments to explore how stomatal densities change and discover just how dynamic plant physiology can be.